Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you everybody for coming. We were taking a bet on how many people would actually show up at the talk. I think I lost. I told them 5 people will show up. And the nature of this talk is such that it may actually get me fired, because one of the main things that I've witnessed as talking to a lot of technical computing people, high-performance computing people, parallel computing developers, is that, frankly, a lot of that work gets done on Linux systems, right? And the situation is such that people in the community end up with a Windows box somehow, and you usually see reasons for, like, why they ended up with a Windows box in this world. It says, well, when I joined the office, that's what was available, or IT forced me, or we couldn't afford a Mac. That's how we ended up with a Windows box. A few people say, I actually like Windows. Thank you, thank you. And the real reason is that because it's the best gaming machine. We all know that, but we don't have to say it to anybody. But how they actually use it, I'm a PhD grad student, I'm a faculty or whatever. I use it for Outlook, PowerPoint, Excel, okay, some gaming. But the technical and scientific computing actually is very little. And I want to show you why actually Windows is a decent box for doing that type of work. So if you look at the general impression, the big elephant in the room basically says that. You've got the enterprise people in suits using Word and Excel, and then all the cool people, hacker community in jeans using Windows. So, and the common complaints I've heard from people are generally around the problem set of, like, I've already learned, I grew up on Linux, it's hard to learn Windows, the shell command.exe from 1982, come on, you gotta be kidding me. It doesn't have my editor, all the muscle memory that I had is no longer there. It doesn't have my favorite IDE that I develop in, my compiler. I'm so used to my compiler options, and I know exactly which optimizations it doesn't do. And oh, if I touch Windows, it's going to lock me in. And there's this feeling of, like, we're not open source friendly. So in summary, everybody's unhappy, and a few people are very unhappy in the right corner. And my hope is that at the end of this talk, to show you that Windows is actually very easy to learn. It's got pretty darn good shells now, including those from Linux, and supports all the various environments that you already use on Linux. And in summary, I hope to make you smile, or at least go from frown to neutral. Okay, how are we going to do this? I personally come from, before Microsoft, I worked at Sun Microsystems for many, many years. And I am too used to my Linux shell. So I want to show you how you can actually put a Unix veneer over Windows, such that everything you've learned, everything you invested in, you can still use it on Windows very effectively. All the investment in the tools, libraries, knowledge, muscle memory, it's all transferable. And a lot of tools and codes and libraries that people use on Linux are now available on Windows for doing technical and domain specialist type of work in this field for scientists. And one of the other things that I'm going to talk about is the fact that you can kick the tires, try Windows, without using some of the proprietary features of Windows. Kind of kick the tires, try it out, without feeling locked in. And the way you do that is you use cross-platform languages. You use C++, you stick to the ANSI standard. You use Python, you use tools like that. So objective is essentially to add to your toolbox and not really take anything away from it. So at a high level, I'm going to break it down into 3 sections. Things that give you a Unix look and feel. You can install it on Windows. Suddenly you feel like you're pretty much on a Linux box. General purpose development environments. These are, if you're a GCC user, Fortran user, Intel's compilers, whatever. These are the tools that are available. And then finally, dedicated CAS systems. Because a lot of people that we deal with are scientific computing people, and they may use stuff like MATLAB and Mathematica. Okay, so let's start diving in. The first system that I would recommend people try is Cygwin. When you install Cygwin, it gives you essentially a choice of several Unix shells, such as Bash, Z shell, Corn shell, whatever your taste might be. And the way it works, this is not taking a Linux application and just bringing the binary over. This is a source level environment for actual development. So you can still use your shells as the installation, after the installation. But if you actually want to port your programs over, you have to have access to the source. And of course, it gives you GCC and a bunch of other compilers, and you can build the environment. So what happens is once you've built your application, there's a cygwin.dll that essentially is the library that you link to, and it does the translations to equivalent Windows APIs. Some of the big applications that I've imported with that, OpenOffice. I mean, that's a major application, and some of the Sun Java environments. Beyond just having the Linux tools, they also have a number of integrations with Windows, such as ACLs, access control lists, and things like that. The next environment that I would suggest people look at is SUA, which is a subsystem for Unix applications. This is actually from Microsoft. It pretty much works like Cygwin. The only difference is, while Cygwin is a DLL, a standard user mode DLL that your application links to, SUA is a full subsystem. This is the Windows NT subsystem, OS2 from way back when, and SUA. They're right next to each other. So while Cygwin would have to do user mode, kernel mode transitions, a lot of this stuff happens at a lower level and is more efficient. But generally gives you the same tools, same environment. The last one, like I said, there's about 5, 6 of these. I'm just going to mention 3 of them just to get an idea. Mks Toolkit is another company that provides a set of well-built and tested Unix utilities and shells. But the thing that it has going for it is a lot of good integration with Windows. This is particularly good if, like, let's say you're a grad student in charge of, you've been demoted to take care of the Linux and Windows machines in the office, and you want to use the same utilities to actually manage all systems. So they have a lot of investment in system administration stuff beyond the usual shells and editors and such. So as I mentioned, as far as the basic stuff that gives you a Linux look and feel, you can use the various shells that come with these environments that I just mentioned. Another option is, hey, if you're not going to do a lot of development and you don't want a full system, all you want is your grep and awk and sed and blah, 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 you can actually install the GNU-Win utilities, and it just gives you about 150 to 200 tools, such that you feel right at home on Windows as if you're on your Linux box. Moving beyond shells and utilities, another thing that has to do a lot with muscle memory, and it's like, I do not want to learn yet another Windows editor, Notepad, or this or whatever. All the interesting editors that are out there are fully natively available on Windows, and they work quite well. So VI, Vim, Emacs, whichever religion you have, they're available in there. There's a bunch of newer batch that do some new tricks they're worth trying. Microsoft's Visual Studio environment itself, if you go to Add-in Manager in the Tools option and search for Vim and Emacs, there are packages that install and give you a very decent emulation of Emacs and Linux and VI. So even if you want to be in Visual Studio, but you still want to have all the keystroke bindings that you want, that you have learned, you can do that as well. So let's actually look at what one of these environments looks like. So if you go to Add Remove, just to show you how easy it is to do this. If you click on the Turn On, can you everybody read that? Okay. Turn on Windows features. I was just talking to one of the Microsoft employees, and even he didn't know that we had this feature. So don't feel very bad. If you go down a few, you will see here Subsystem for Unix applications. All you have to do is click that, and after 2 minutes, you have a pretty decent environment with several shells, editors, GCC, 150 to 200 tools, and so on. So any of the environments that I mentioned will give you all the standard tools, and most of them work pretty decently. The Suo one I mentioned just because it's already on your system. You just have to click, and it works well. It also has pretty darn good integration with the Windows for System Administration world as well. So the idea was that you just don't feel like you've got Linux on Windows, but you want to see what does Windows add that actually might be interesting as well. So the improvement to command.exe from 1765 that was first written is PowerShell. So this is the new Microsoft shell. You can say, let's say, what was the file? Get content is kind of like cat. You just dump a file. The difference between PowerShell and the Unix shells are, Unix shells normally just work on textual items. You pump lines into different stages of a pipe, and then some human readable output device at the end of it, potentially. The PowerShell difference is that it actually deals with objects. What do I mean? So looking at this program, I can pump it to get member. I can actually fully type these in. And these are all the methods and properties that can be applied to these objects that are coming across, which happen to be lines. But this could be programs, this could be complex files, this could be a spreadsheet, for example. So let's say I want to sort that file. I could do something like get content, pipe it to get member, and let's say we want to sort it, grep -i length. Let's see if there's such a thing. And we see, yeah, there's couple of methods and a property. One of them is called length. By the way, I did something interesting here. This grep actually was not part of PowerShell. This came from the Linux tools that I installed earlier. So you can actually mix and match whatever you need for a better experience of this stuff together. So here in this case, I will go ahead and see that we have a length. I will send it to the sort program. $_ gives you the current object, and there it is, sorted by length. So it's very easy to actually mix and match what you need. If you're doing a lot of generic stuff, you can use the Linux tools. If you're doing something more windowy, you can drop into PowerShell and use PowerShell to use it for what it's very good at. Actually, one more thing I was going to show you since we're here. So remember I said it works beyond just textual stuff. You can actually deal with objects a lot. So you might be a scientific computing guy or a researcher, does a lot of stuff, gathers data, perhaps on Linux boxes. Then you want to bring it in and you want to analyze it in Excel because the model that somebody else gave you runs in Excel. This, I'm going to show you how to actually script this stuff using Excel. So let's say you say new object. By the way, tab completion for all the methods and things that are available as well. Let's say create a excel.application. So E now holds a handle essentially to an Excel object. What does that really matter? So I go pump the Excel object into get member and show me what it's got. And here, the name, member type, and definition, it's the entire Excel object model at the command shell level. This is beyond just pumping lines of text around. You can actually do stuff like stuff data into the Excel sheet, bring stuff out, add a chart to it. So whatever your particular program exposes, you can actually show it. So let's make the Excel visible. So somewhere in here I should have an Excel pop up, and here it is. And we see that it's blank, which is pretty useless. So let's add a workbook to it. Let's see if there's an add method or maybe a worksheet, workbook method. Great. And let's see what methods and properties it has. Add, that's a good one. Let's hit that. Oh, here it is. We've got a sheet. And notice there are 3 sheets. So let's see if we can add a sheet of our own. That has an add method too. If I add it a couple of times, we see that we got a bunch more sheets. So essentially, it allows you to do manipulation of objects very, very easily. Let's add something. I see active cell, I believe, is the current. And we see that Cartagena has appeared up here. So pumping data in, taking data out, manipulating objects beyond a single line of text is stuff that PowerShell is particularly good at. Okay, so now let's go back to our presentation. Bottom line is you've got several choices for giving your Windows box a Unix look and feel, and there are things in Windows that you can combine with it for a better experience. So now that I've set up my environment, I feel comfortable in it, I don't have much of a learning curve, then next obstacle that I see a lot of technical computing people and academics specifically complain about is the lack of their favorite IDE. The top IDEs, you know, this is based on my experience, are usually Eclipse, something like a Python environment, maybe Sage Math, Visual Studio, and an R environment. I've picked these 5, and they're all available on Windows. They work well, quality ports or direct implementations. Eclipse basically started as a Java environment, and now it supports C++ and Fortran and a number of others. Works well on Windows, Linux, and Mac. So if you want to stick to an environment that's available all 3, if that works for you, great. Ipython, I'll talk about it a little bit more later, but it's a REPL, a read, edit, print loop environment, enhanced editor experience, and it's got some parallel computing features as well. Sage Math works with Ipython, works in a web, and it's very good for symbolic math work. Visual Studio is like a Swiss Army environment for writing native and .NET code. And there are several R environments. You can get the plain R. R is another language that, another dynamic language that people use especially for stats work. Very strong stats libraries. And a company called Revolution Analytics actually put a plugin into Visual Studio that supports the language, supports debugging, visualization, and everything. It's a very nice port. And it says, of course, Emacs. Emacs, as we know, can be programmed to do anything. So if you love Emacs, you can stick your whatever compiler you like in there, and it works great. So this was the IDEs if you're an IDE type person. Some people might say, hey, I'm not really an IDE guy. All I need is my shell, VI, make, and I'm good to go. So the build environments, the MKS, Cygwin, SUA, etc. that I mentioned, they all have a complete set of compilers and tools for building stuff. Another one I would recommend people look at is MingGW. MingW is an environment that's different than the others in that they've taken GCC, modified it, such that it generates Windows binaries that link to the Windows and C++ runtime. So these are complete Windows self-contained binaries. It's interesting if, again, you want to stick to GCC, but you don't want to go through any of these emulation layers of any kind, and you want to have a genuine NT binary. So MingW enables you to do that. Up to now, it was just 32-bit. We're helping them actually make a 64-bit port to Windows. Another important thing is I would highly recommend that you stick to cross-platform compilers. This would be, again, GCCs of the world. It would be Intel, C++, and Fortran, PGI, Fujitsu, etc., that have tools that work well on all the operating systems. Scripting, make, nmake, all of those stuff, again, are available on Windows. One of the ones that I recommend people look at is CMake. CMake is unique. There's an example of the syntax up here. In that, yes, you have to learn a new syntax, but once you learn it, is pretty configurable, and with the push of a button, you can have it generate a Visual Studio project file, you can have it generate a Linux make file, you can have it for any operating system, any particular derivation. So it makes life easy. Like you might be, again, a researcher that have some Windows people, that have some Linux users, and you don't really want to constantly update two separate build environments. CMake is good for that. All right, so we've got our environment, we've got our editor, et cetera, et cetera. What about languages and compilers? Kind of like VI and Emacs, the classics for technical computing are C++ and Fortran. So the companies, again, I would highly recommend you stick to are Intel and PGI. When it comes to raw number crunching, Fortran still is the king, although not many new graduates learn Fortran. It is usually forced upon them because of realities of life. But it turns out that for pure number crunching, Fortran is still the king. So if you do a lot of that stuff, consider Intel or PGI's compiler. And of course, C++, you've got several choices there. Newer on the block, and I would put this in the either dynamic or the more productive, more modern languages, it's things like C#, Java, Python, R, F#. By the way, if you're here for the demos tomorrow, make sure you go to Christoph's F# presentation. It's going to be pretty good. And of course, the dedicated CAS systems, the MATLAB, Mathematica, Maple, etc., that we'll talk about shortly. So you've got your editor, you've got your environment, you've got your compiler, you've got your languages. The next step is libraries. You know, programs don't just compile by themselves, right? Usually they call into a library of some sort. So I'm not going to list them because there's too many of them, but key ones like Boost and NumPy and SciPy, etc., are all available on Windows. A lot of this stuff are open source and freely available, so there's a very easy way to get them and use them. For high performance computing, you know, MKL, IMSL, NAG libraries, Visual Numerics, Atlas, etc., are all available on Windows, work identically to their environment in Linux, so it should be very easy to port your programs that depend on these libraries. Runtime libraries that allow you to do parallel computing, things like OpenMP, MPI, CUDA for GPU programming. Again, these are available in the Microsoft compiler, in all the Intel and PGI compilers, and for CUDA, you know, NVIDIA has the latest, best drivers available, and they've got a very good plugin into Visual Studio for doing debugging and profiling. And for data management libraries, there's plenty of those as well, NetCDF, HDFI readers and writers. All right, so I've got my editor, my shells, my compilers, my languages. Now I build it, and nothing works. I need to debug it. After I debug it, it doesn't run very fast. I need to profile it, etc. All the ones that I mentioned that work with Visual Studio come with a native debugger and a profiler. Graphical profiler, it can show you this is exactly the HUD function. They usually both have IP sampling and code injection at the routine level types of profiling. There's a free and open source plugin for Python that gives you MPI profiling and debugging. If you need to do let's say you've got a cluster of 128 nodes with InfiniBand, and there are major traffic going on, and some nodes are always late. You want to find out what's going on. If you've used dtrace on Solaris, the equivalent of that on Windows is called ETW, Event Tracing for Windows. You run that, you get a standard OTF file, Open Trace Format file. It's an open standard. And you pump it into something like Vampire or JumpShot, and it gives you graphs like this that basically give you processor versus time, and you can see the communication patterns. You can zoom into slices, and every send or receive that was done, you can figure out what's going on. You have high-level views that basically say how much time was spent in your application versus the communication library, so you can figure out where to focus. And there are other things like Marmot and ISP where they trap MPI library calls and analyze it for errors, for format issues, for parameter mismatches, and so on. All right, so far this was generic programming. You might be C++, you might be Fortran, you might be Python, and so on. Other environments or integrated development environments for engineers and scientists are things like Maple, MATLAB, Mathematica, and so on. All of these, again, these are the Windows ports. I think mostly Windows ports. I just did screenshots. So Maple, symbolic execution environment, MATLAB more matrixy, but they're encroaching on both. In fact, I think Maple used to be a plugin that was available for MATLAB for doing their symbolic work. Mathematical, mostly symbolic, very popular with physicists. And Sage uses Ipython to give you a web-based, very nice environment for doing symbolic math. So it's mostly for math. Ipython, a generic Python environment. And Octave is again, open source, free. All this stuff is open source and free version of MATLAB. It doesn't have all the bells and whistles of MATLAB, but if you can't afford, $5,000, $10,000 an environment, you can use Octave with reasonable success. These are all freely available. These are commercial. The ones that have a little star next to them have the added feature that they work with Windows HPC. So if you have a particular job that runs for many, many hours or maybe days or weeks, you can just install Windows HPC and press a button, and it knows how to distribute it. It's particularly embarrassingly parallel stuff. Okay? All right, so this was so far a tour of everything that was important to a developer, domain programmer, domain specialist, that can, from the look and feel of Linux to all the programs that I need, to all the development environments I need, I can set up my machine and do some work. So if you do actually set up your machine beyond Outlook and Excel, these are some of the things I would recommend they actually look at that are on the Windows side that I think would enhance your experience. Visual Studio, F#, the language, things, libraries like Mpi.Net, Python, and PowerShell. There's many more, but I just picked those for the sake of brevity and time. VS, I'll summarize it as saying it's a state-of-the-art development environment. I've used pretty much all the major ones, and I still think VS is one of the best ones out there. In fact, when I was working at Sun Microsystems, we had this dirty secret that in my group, which was the compiler optimization group, I would get bills for Microsoft environments. I said, what's going on here? So my engineers would basically say, well, it's much easier and productive to work in that environment to build a compiler, and then we'll compile it with the Sun OS compilers. The Sun OS compilers were very slow, the debugger, very slow. It's gotten better over the years, but back in the 90s, the good days of Sun, I kept getting bills for Microsoft Visual C++. It's a very productive environment, IntelliSense, et cetera, et cetera. And more importantly, for hardcore technical computing, parallel computing people, the major vendors all have native plugins for Visual Studio with debuggers and profilers. Basically, this just makes you do your project in a shorter time, which is critical. Time to market, time to release your papers is critical. It's beyond just like a nice-to-have thing. It's important to note that essentially if you're an academic, you can get this stuff for practically free. If you're a startup of some sort, you can go to the BizSpark program and get essentially all the important stuff that Microsoft provides for free. F#, I won't say much about it, but basically it's a functional program, multi-paradigm programming language, runs on top of .NET, but it runs on macOS and Linux as well, thanks to Mono Miguel de Icaza's project. It's open source, it's free. One of the things I would check out. Christoph, will you be doing units of measure demo? Okay. Okay, yeah, so go to Christoph's demo, he might show that. All right. Another one that I think is very interesting for scientific computing type people is Python. It's gone from being like number 22 on the funky TOB index to being number 3. It's becoming very popular mainly because it's very easy to learn as a CS 101 language all the way to doing your PhD thesis in. Amazingly deep and wide set of libraries for whatever domain you might be in, bio, finance, whatever. And this environment essentially gives Visual Studio a MATLAB look and feel. So actually at this point, I might demo that. Let's see if my connection back to Redmond is still up. Oh, I've been fired already. They worked very fast. Okay, so the way you get this, let me go to, so you go to Codeplex, which is the open source environment, and you go to downloads and press install. Takes less than a minute, and you're good to go. This is what it looks like. Okay. Here I have the standard editor for Visual Studio. You have a shell that might be any version of Python you might like. Get IntelliSense on everything. Let's do it here. Say from, as soon as I hit that. By the way, this might look a little sluggish. It's actually pretty fast, but I'm on a remote login from sys import. So as soon as I hit the space bar, you can see all this stuff. Again, this is a free open source plugin. It's standard Python, does not lock you in any way. But the bringing together of a standard language and the capabilities that Visual Studio gives you just makes you a much more productive Python programmer. So this program in particular is an MPI program for computing Pi. And it's kind of like a hello world of Pi. So the way I'm going to actually connect this to a cluster and actually do some computing is, let's look at the properties first. So you've got several debuggers that are available with this environment. Standard Python debugger, you've got an MPI debugger. Here, the name of my cluster is called LATAM. It actually goes to the Active Directory, finds out all the clusters I have, gets the information about the machines that are available. In this case, there's about 6 or 7 nodes, I can't count. And I can actually select which nodes I want my program to be debugged on, maybe because those have GPUs and I'm using Pi CUDA or whatever. In this case, let's just go ahead and use everything that there is. Then I can go back to my program. And I have a breakpoint set up here, and essentially all I have to do, and let's look at, and this is the Hpc Job Manager that shows you what jobs are running on the cluster. I can't read that far. Okay, great. So I'm going to just hit F5, and it says I have an error. Excellent. What did I do to it? Oh, yes. I don't really need this. Hitting F5, if you notice in this window, it's submitting a job to the, I don't know if you can read that, but basically says job submitted to the cluster. Let's see if we believe it. Yeah, here it is. The MPI debugging session has been started. Okay. And here I am in my program. And I can hover over variables and expand them and look at their data, the fields in the structure as if this was a C++ program. Again, this is a free open source plugin, but because of the features and the ability to parallelize on a cluster that the Windows environment gives you, it just makes it that much more productive. The rank, which is for SPMD programs, the most important thing you want to keep track of. If I hit F5, if you notice the rank is changing to 7, to 3, and the arrow here is moving around as each of the ranks hits that particular breakpoint. So I keep hitting F5, and it finishes. And I didn't capture the output, but I think we calculated pi to be somewhere between 3 to 4. I'm not sure exactly. So that was a quick example of how you can marry some of the open source stuff and enhance them in the Windows environment. Okay. Another environment that I want to highly recommend people to use, let's say, okay, Visual Studio is nice, I've got a bunch of plugins, but I don't want to use Visual Studio for whatever reason. I wanted to stick some environment that's identical across everything. For Python, I would highly recommend you use Ipython, which is an enhanced shell that it also happens to have parallel computing features whereby you start engines on different nodes on a cluster and you connect to it and interactively submit jobs or do a map of a function across multiple nodes. It has support for Windows HPC, for PBS, for a bunch of Linux schedulers as well, and it's obviously open source, available on all 3 platforms. Okay. I'm a Python fan. I'm not going to preach too much about it, but I think as being a lot of academics here, you know, there used to be a time where people taught Visual Basic or something as the first programming language. I highly recommend you consider Python. The tools are great, the libraries are great, the ecosystem is very vibrant. We are a big Python sponsor, and I think the language has a lot of good things going for it in the future. And by the way, the environment that I showed with Visual Studio works with any Python environment. It could be IronPython, which is the .NET version of Python. It works with CPython, which is the native version of Python, or Jython, PyPy, whatever else. Other interesting things I was going to quickly talk about is, like, again, if you're a .NET programmer and you want to do some high performance stuff, there are things like Mpi.net, which are wrapper libraries, high performance wrapper libraries for Mpi libraries. If you wanted to, let's say, have a program that asked all the hosts, all the nodes in a cluster, what is your name? Get the names, sort them, and print them. This is what the C code would look like. Of course, you can't read it, but half of it is memory allocation, and you could +1 errors and so on. The same thing using Mpi, C# and Mpi.net looks like that. You get a communicator, you do a com.gather of the environment and processor names. Well, you allocate that. And then if your rank is 0, which means you're the first instance, you do an array of sort of the host names and print it out. That's how easy it should be. This one, you can't even tell what the program is doing until you go and throw everything else out. The way the Mpi.net, by the way, gets its high performance is that, unlike the JVM, .NET allows you to do a bunch of tricks like unsafe code, quote, unsafe, do a fix such that you stick a handle to a particular area in memory and tell the GC not to move it. And then if it happens to be one of the standard MPI types, you just go ahead and does a p invoke into the MPI send, the native MPI send. Otherwise, it serializes. Like in the Java wrappers for MPI, everything gets serialized blindly. As a result, for the famous NetPy performance, you can see that C and C# essentially have identical performance behaviors. Because for most native types, all it does, check and call the native environment anyway. So let's see, you have drank the Kool-Aid and you've come to Windows and you say, okay, what else does Windows have? Show me very quickly how I can learn it. I would recommend a project called Parallel Dwarfs, again, open source project that teaches you how to do parallel programming with every language, small, medium data types, large data formats, and any particular runtime environment. What code? We took, well, they took the dwarfs from Phil Kalila's environment, a paper that basically has all the standard core algorithms for HPC embedded, the spec benchmark, machine learning, etc. And they parallelized every version of this using OpenMP, using MPI, using this, using that. And so essentially for each native and managed environment, for each of these programming models, for each of these data sizes, run it, you run the program, you trace it, you plot it, and you show results. This is good for teaching, this is good for analysis of mixing stuff together, and this is, for example, a structured grid project, and then at the end you get results of what the runtime behaviors were like. You also get detailed trace information that you can analyze, see what the cache behavior was, et cetera, et cetera. And so JumpShot and Vampire have already mentioned high resolution InfiniBand type performance between nodes traced and clock corrected between processes. So far it's been mostly on-premise, local cluster, local parallelization. For this part of the last part of the talk, how much time do we have? Perfect. I want to actually ask my colleague, Felipe Ayora, to come up and help me out. Want to introduce yourself?
My name is Felipe Ayora. I work in the Windows HPC server group. We put together basically what's HPC Pack. Windows Server together with HPC Pack is what we call the Windows HPC Server Suite. And HPC Pack basically allows you to run computational problems in parallel, and like we're going to show, actually even on the cloud, very, very easily. And the first thing I remember you said is you wanted to be at the beach all day long here in Cartagena.
Yes, yes, preferably. So yeah, so I would love to have a laptop that's connected to cloud and runs all my stuff over there, so I don't have to have a $1 million cluster around. So let me tell you one of my problems. We're going to act this out. I'm a scientist. I'm an astronomer, and we've got a bunch of star telescope data that comes in, and we want to do some improvements to the images. These images come and they're very patchy. They have seams, and there's actually a lot of correction and prep that needs to go into these images. We can do it on a local box. It just takes forever. We're talking months, weeks or months. So we want to see how you could help us do it out on the cloud, so I can take my laptop to the beach and connect it to Azure. Can you help me?
Actually, we can.
Excellent. So let me show you what my problem is.
The beach?
No. I found a beach. Let's find a famous star area. Horsehead Nebula. Everybody knows the Horsehead Nebula. This is, by the way, Worldwide Telescope. Okay. So when we get all these data from different telescopes, this is how they come in. If you can see, it's a different color. It's not what the color the eye sees. It's got seams. It's very patchy. And what we really want to do is do the processing that allows us to turn that image, which there will be millions of them, into this, which is what the actually, if you look at through a telescope, that's what you see. So there's a lot of image processing, raw image processing, matrix operations, and so on. So I know our team has given your team the code, and if you could just show us how we can parallelize this and run it on the cloud, that would be great. All right, so, and we see that our cloud has moved, oh, here it is. All right, so show us how it works.
Okay, I've talked with a few of you, and I know you, some of you use HPC Pack, but this is basically the main console. That's the administration console. And when Sean said he wanted to run a very, very big job, I immediately thought about the cloud. What I prepared for you, Sean, is basically 40 nodes up on the cloud, extra large nodes, 8 cores each, for a grand total of 320 cores.
Wow.
This was surprisingly easy to put together.
So where's my head node in this?
Your head node is the only thing that's on premise, and that could be a laptop. That's exactly what I'm going to be demonstrating tomorrow. In this case, it's the head node that you have in Redmond, right?
Yeah. Okay.
So
can you show me like a pictorial view of this stuff?
that is the beauty of it. We, aside from the normal list view where you can do a lot of the actions to manage, we have fully customizable heat maps. In this case, what I've chosen for you is 2 performance counters. At the top, you see CPU utilization, which, of course, being idle, is very minimal, and disk throughput. So the nice thing about it is that you can customize the colors and the performance counters, and these are pretty much the basic ones.
So this is kind of like ganglia.
Very much like Anglia. If you're familiar.
I understand ganglia.
Got it. Okay, so now, as we said, 320 cores. The nice thing about it is if you look on this side, you can group them. So we're not just looking at your Azure nodes. You can also have nodes on site. In this case, you don't, because you want to run this big job on the cloud.
But I could have my laptop, 4 nodes locally, test my application, and every month when the telescope data comes in, yes, I can press a magic button and it goes to the cloud.
Exactly. Or you could start running it to make sure it's going in the right direction.
Okay.
You like it, you burst to the cloud. And it's surprisingly easy. For example, we were looking at the nodes here. To add a node, you just go Add Node, select the Windows Azure node, click Next, and just select the number of nodes you need. There's a very quick initial configuration to give the data about your Azure subscription, but that's it. So it's very, very easy to add nodes.
So as far as my program is concerned, is it transparent to it that some nodes are local, some nodes are in the cloud, or do I have to change my programming style?
Transparent.
Okay, so it just talks to the scheduler.
Yes,
like that.
that's what Hpc Pack does for you. Basically, it has a scheduler and some deployment tools too for.
And how do I
certain
bring
tasks.
nodes up and down?
That's a beauty too. Let's say you don't want to run it in all of them at the same time. You just select a bunch of nodes.
We're very bad actors. I can tell. Sorry about that.
I thought we were doing it. And just
We need more drama.
take. Well, let's say you're having a beer.
Okay.
And you just want to run in a few of them. You just take them offline.
Okay, so I just click on take offline.
Take offline, and they'll become.
Now, does that mean Azure takes them away, or
No.
they just?
They're just not available for scheduling. They're still
I
up
see.
and running on the
And what if
cloud.
I wanted to give them away? Oh, that's the shutdown, or?
Yeah, if you
Or stop.
if you would click stop, and then you would take them all away.
Okay. Okay. So let's run the program, see if it actually works.
So to make it even easier, and to make sure that this demo would go quickly, we put it all in a script. So ready to run your script?
Sure.
Okay.
So let's see the heat map, because
Yes, that's what I want to show you too. The proof that it's working. So data is coming down from the cloud down to the server that we have in Redmond. And as you're going to see the performance counter start gathering the information from those nodes up in the cloud and firing up. Of course, CPU utilization is the first thing we see. So there's the proof. We made it work.
I haven't seen anything change. Where's the proof? They're the same colors to me. Here's the drama.
They keep changing, trust me.
Oh, okay, okay.
There you go.
Yeah, okay, all right.
Yeah,
So
we've
the blue
optimized the
means-
refresh rate for it not to be too costly when it goes up and down.
I see,
from
I
the
see.
web.
Okay, excellent. Okay, well, thank you very much. This is fantastic.
Thank you.
Excelente.
And if you want to see this in person, come see me, booth number 13 tomorrow.
Excellent. Thank you, Felipe. All right, we'll let that run, and I'll quickly try and finish. All right, so we talked about this already. So I'll kind of conclude by saying, having been in the Unix and Linux world, still using them, and living in the Windows world, these are the things that, in my humble opinion, are worth checking out, such that you can combine them together for a stronger toolbox as a scientific computing person. I think Visual Studio, despite some of the learning curve, is worth it. Get the Vim, get the Emacs emulation, stick to a standard language. If you want to be a little bit more brave, C# and F# are excellent, highly productive languages for scientists. Things like Mpi Net that I mentioned, GPUs, obviously, for this general zip code are highly, highly useful. The best drivers, the best development environments, such as Nsight, are available on Windows. If you're doing any scientific Python work, Visual Studio is a fantastic environment for it. The CAS products, such as MATLAB, Mathematica, et cetera, that I mentioned, the primary markets that they sell to are Windows, so usually the best ports are there. Domain specialist support in general, if you want to do some scientific stuff with things like even Excel, there's lots of support for you, lots of add-ins. Even the Windows Hpc product, you can give it an Excel sheet and say run, and it runs it on a cluster for you in a parametric sweep or Monte Carlo style. If you have a UDF, a user-defined function in your Excel that does number crunching, you can tell the HPC system, say, hey, from Excel, say this is UDF is HPC safe. You send it to the cluster, and you can use SOA-style calculations for it. I think the Intel and PGI compilers, again, environments, work best on Windows because of the Visual Studio integration. And .NET in general, if you're a JVM user, I think .NET is got some features that are well ahead of a JVM. And even things like generics are done better, and you have more control over what behavior of the VM is. So in conclusion, if you haven't already, and you're a technical scientific computing type person, give your Windows box some love. I think you'll be surprised what cool things you will find in there. beyond just Excel and Outlook. You can leverage all the investments you've already made, muscle memory, know-how, 20, 30 years of using Linux. All that stuff transfers over very easily. And my advice is stick to the cross-platform languages when you're kicking the tire, and you can enjoy the experience without feeling locked in. And it's not really a trademark. I made that up. And it's the best features of Linux and Windows, in my opinion. And that's how I work, and it works for me. I hope you'll give it a try. That's it.
We have time for a few questions.
Yeah, thank you very much. That was an excellent presentation. I'm particularly interested in this offloading HPC to Azure. How does that work if your application or your MPI application you're running anyway is dependent on large volumes of data?
So very good question. He would say, how do you do the data problem with on-site, off-site? So first of all, as far as the bursting support, in the latest version, there's 3 ways you can actually use things. One is the standard cluster that's traditional clustered locally. You can also take a bunch, even if you don't want to invest in a bunch of clusters, you can take a bunch of Windows boxes, rope them, and say, I want these 50 machines that are sitting at night idle to be my cluster. So you can do an ad hoc cluster very easily. And you can also say, I want to go into Azure and get my 300 nodes. So you can, at the maximum, you can have a local cluster, bunch of workstations that nobody uses at night, and Azure for like the most complex environment. Currently, the MPI stuff that's in beta internally works purely in the cloud, right? They're upgrading Azure to have high-speed networks for MPI-style programs such that you can have dedicated clusters. And for that, obviously, you don't want to have a lot of data going up and down. You pre-populate your data in the Azure storage, and then you go ahead and say, go up there. But ideally, you want to have a tiny cluster or some of those Windows boxes that I mentioned to try it on 4, 8, and then by induction, it should work on 64, 128. It never does, but you can at least start debugging it.
No more questions? So thank you very much again for
You're quite
a very good presentation.
Thank you.